Welcome to the Walton Pi. Today we're going into my third video in my AP Precalculus series where I am covering all the different topics in the AP Precalculus course that will show up on the AP exam. Today we're talking about section 1.5, Polynomials and Complex Zeros. Now this is one of the sections that a lot of students in my experience have trouble with, so I've decided to make an extra long video going extra in depth. So I hope that this is helpful. If it is, please like and subscribe, but let's get started. So most of us first learned the numbers 1, 2, 3, 4, and so on when we're counting, okay? These are what we call the natural numbers. It's natural to start at 1, then go 2, 3, 4, and so on. Then we learned about negative numbers and fractions. And then eventually we learned about all real numbers. So numbers like pi, e, all of these are weird numbers that have these infinitely long decimal trains, and those are the real numbers. Today we're introducing the next group of numbers, okay? These are called the complex numbers. They're complex because when people came up with these, they were like, this doesn't make sense, this is complicated. That's where the name complex comes from. So up to now, when you've had a negative number inside of a square root, we've said that the answer did not exist. Or if your teacher was being very precise, they'd say there is no real answer, because the real numbers, those are the numbers that we see all the time. If you have the square root of a negative, that's not a real number, but it is a complex number. Okay, so these complex numbers, that's what we're going to be diving into and talking about. What does it mean if we have a square root of a negative? Okay, so complex numbers allow us to take the square roots of negative numbers. Okay, the simplest negative number that we're going to deal with is -1. So we define the square root of -1 to be the imaginary number I. It's called imaginary because when they were first discovered, they were saying, look, these don't make sense, so we're just going to pretend that this is a number and then see that everything works out, hence why they get the name imaginary numbers. They work really, really well. If you go into electrical engineering, you really need to know imaginary numbers. So things like that, they're very real, but that's why they're called imaginary numbers. Okay, so we are going to say that the square root of -1 is the imaginary number I, and that means that the square root of -4, that's going to be 2i. Now, complex numbers, those are just the sum of a real number and an imaginary number. So it's going to be something like 3 plus 7i, or -1.2377 plus 0.314i. We just have a real number plus a complex plus an imaginary number, and that gives us a complex number. And then we also have, if our complex number is a plus bi, there's also this term called the conjugate, or the complex conjugate. So the complex conjugate of a plus bi is a minus bi. You just change the sign that's attached to the imaginary piece. So now let's talk about zeros of polynomials, okay? A polynomial p of x, the zero of that polynomial is any real number a where p of a equals 0. So it's also called the root of the polynomial, p of x is 0. Those are two different terms that essentially mean the same thing. So let's say that p of x is x minus 7 cubed times x squared plus 1 squared. P of 7 is 0 cubed times 8 squared, which is 0. That means that 7 is a 0 of the polynomial p of x. For polynomials, knowing that x equals a is a 0 of the polynomial p is equivalent to knowing that x minus a is a linear factor of the polynomial p of x. So in a polynomial p, if a linear factor x minus a shows up n times, we say that the corresponding 0 of p, in this case a, is going to have a multiplicity of n. Multiplicity tells us how many times does this show up, how many multiples of x minus a are in that polynomial. So you can think of multiplicity as the number of ways that that specific number is forcing the polynomial to evaluate to 0. So in our polynomial, p of x is x minus 7 cubed times x squared plus 1 squared. The factor x minus 7 shows up 3 times. So that tells us that 7 has a multiplicity of 3 as a 0 of our polynomial. Now the multiplicity of a 0 of a polynomial p also tells us information about the sign of the function near the 0. So if the multiplicity of a 0, x equals a, is even, then on either side of x equals a, the signs of the values of the function are the same. So either they're both positive or they're both negative. So in p of x is x minus 7 cubed, the x equals 7 is a 0 with multiplicity of 3. This means that on either side of x equals 7, the signs are going to change from one side to the other. So if it's an odd multiplicity, one side is negative, the other side is positive. So if we look at the graph of this function, out there at 7, it goes from being a negative value to a positive value. So that's what it means. So that's information that we get from knowing that this is a 0 of multiplicity 3. Now, complex zeros. This is where a lot of students get messed up. And so this is a really important topic that is going to be pretty important later on. Okay, so in our polynomial p of x equals x minus 7 cubed times x squared plus 1 squared, we've factored this as much as possible over the real numbers. However, over the complex numbers, we can factor a little more. Okay, so the roots of the quadratic x squared plus 1 can be found through the quadratic formula. So x equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. There's a lot of different mnemonics to remember that, but however you remember it, we can just plug those values into the quadratic formula. So here we get negative 0 plus or minus the square root of 0 squared minus 4 times 1 all over 2 times 1, which gives us negative 2i over plus or minus 2i all over 2, which is plus or minus I. So that means that x squared plus 1 factors as x minus I times x plus I over the complex numbers. So we can further factor it all the way out to p of x is x minus 7 cubed times x minus I squared times x plus I squared. So that means the complex zeros of p of x are 7, I, and negative I. The real zeros of p of x are just 7, but the complex ones include I and negative I. Just as real zeros have multiplicities, complex zeros also have multiplicities. So in this case, both I and negative I have a multiplicity of 2, since x minus I and x plus I both are raised to the powers of 2. So that means that we have all of our complex zeros, we have all of their multiplicities, and the nice fact that we can use is that all polynomials factor into products of linear complex terms. So we can break down any polynomial into x minus something times x minus something times x minus something and so on, where all of those somethings are just complex numbers. Sometimes they're going to be real, but they are always going to be at least complex. A useful fact that goes along with that is that if a polynomial p of x has degree n, meaning that the highest power of x is n, then there are going to be exactly n complex and real zeros of p of x where we count multiplicities. So our example polynomial p of x is x minus 7 cubed times x squared plus 1 squared. If we expand that all the way out, we get this nasty thing. However, we notice that the highest power of x is 7. So since the highest power of x is 7, that means that p has degree 7, so there are going to be exactly 7 zeros of p of x. So the zeros of p of x are 7 with multiplicity 3, I with multiplicity 2, and negative I with multiplicity 2. We add those up, 3 plus 2 plus 2, that gives us 7 different zeros, and so that actually checks out with what we were looking for. Now, if we see a polynomial in the form where it's factored out, like p of x equals x minus 7 cubed times x squared plus 1 squared, the degree can be found just by finding the highest power of x. So we have an x minus 7 raised to the 3, so that's the degree of 3. We have an x squared plus 1, that's degree 2, raised to the 2, so that's 2 times 2, so that gives us a degree of 4. And we just add those together, 3 plus 4, to get the degree of 7, which is our degree of p of x. Now, if we're given points on the polynomial, finding the degree can be a little bit more difficult. However, we can use a table to find it. So let's say that we are given this table that matches up with some polynomial. So when x is negative 3, f of x is 133. When x is negative 2, f of x is 22, and so on. This is the plot that matches up with a polynomial, but we're trying to figure out what's the degree of this polynomial. What we can do is we can look at, is this degree 1? So remember, if it's degree 1, then the difference between the average rate of change is going to be the same. So when we go through and are calculating that just by looking at what's the difference. So to go from 133 to 22, we have to subtract 111. To go from 22 to -5, we subtract 27. And so we can check and see if they're all the same. That tells us it's probably degree 1. In this case, they're not. So we just go through and figure out what is everything. So we got that. And now to check, is this degree 2, we repeat the process. So we say, okay, what are the successive differences? To go from -111 to -27, we added 84. To go from -27 to 3, we added 30. To go from 3 to 3, we added 0. To go from 3 to -3, we subtracted 6. Then we added 12. Then we added 54. So this is not degree 2. To see if it's degree 3, we do the same thing. And we see that this is -54, -30, -6, +18, +42. It's not degree 3. Then is it degree 4? Well, add 24, add 24, add 24, add 24. All of these are the same, so that means that the degree of this polynomial is most likely 4. It doesn't tell you what that polynomial is, but that is how you would be able to find the degree. So if you're ever really confused, look at successive differences to try and figure out what the degree of this polynomial would be. So let's go over a couple examples. Let's look at the polynomial f of x is x to the 4 plus 5x cubed plus 6x squared minus 3x minus 9. That looks like this. If we graph it, we see that we have some x-intercepts at x equals -3 and at x equals 1. This tells us that x plus 3 and x minus 1 are linear factors of f of x. And then we can go through polynomial division, which is in section 1.11. So if you haven't learned it yet, check out that video, which will come out in a few weeks. And then we can be able to factor f of x as f of x is x minus 1 times x plus 3 times x squared plus 3x plus 3. The quadratic formula further factors x squared plus 3x plus 3 as, if we go through the full quadratic formula, we get -3/2 plus or minus the square root of 3 all over 2 times I. Okay, it's an ugly complex number, but it is a valid complex number, and those are going to be the roots. So that means that f of x factors as x minus 1 times x plus 3 times x minus parenthesis -3/2 plus the square root of 3 over 2i close parentheses times x minus parenthesis -3/2 minus the square root of 3 over 2 times I close parentheses. Each of these linear factors appears only once. That means that each of these zeros, both the real ones and the complex ones, have a multiplicity of 1. And the real zeros of the polynomial tells us information about the inequalities that involve the polynomial. So if we are solving f of x is bigger than 0, the real zeros of -3 and 1 are the only two endpoints on the solution set. -infinity to -3, union 1 to infinity. And if we were to look at f of x is less than 0, it would be -3 to 1. Now, the two polynomials we've seen so far both have had two complex zeros. First, we had p of x is x minus 7 cubed times x squared plus 1 squared. Those had the complex zeros of plus or minus I. And then f of x equals x minus 1 times x plus 3 times x squared plus 3x plus 3 had the complex zeros of -3/2 plus or minus the square root of 3 all over 2 I. Note that in both of these cases, the two complex roots are going to be complex conjugates of each other. This is not a coincidence. This is actually always true. And the reason for that is if a plus bi is a zero of a polynomial over the real numbers, meaning all the coefficients are real numbers, then its conjugate is also a zero of the polynomial. It turns out that that has to be the case. Otherwise, you're not going to only have real numbers as the coefficients of the polynomial. So that means if I tell you that the polynomial x squared minus 6x plus 25 has 3 plus 4i as a zero, you can immediately tell me that the conjugate 3 minus 4i is also going to be the zero of the polynomial. Now we're going to switch gears just a little bit. These are just some other terms that we need to know, and they're just included in this section. We say that a function is an even function if it is symmetric across the y-axis. So this means that f of x is f of negative x for any x you put in. And then we say that a function is an odd function if it is symmetric about the origin, meaning you can rotate it 180 degrees around the origin and it looks exactly the same. This means that f of x is negative f of negative x for all x. And these names actually come from how polynomials behave. If every power of x in P of x is even, then P of x is an even function. If every power of x in P of x is odd, which means that the constant function, or the constant term in the function must be 0, then that means that P of x is an odd function. So this function is symmetric about the y-axis. That means f of x is f of negative x for every x, so this is an even function. And then for this function, if we rotate it 180 degrees around the origin, it looks exactly the same. So this is an odd function. I hope this was helpful in understanding both even and odd functions, as well as the much bigger topic of complex zeros, complex conjugates, all of those different things and how they all tie together with functions. I really hope it was helpful. If it was, please like and subscribe. It really helps me to keep making these videos. And feel free to check out the other videos I've been making on this topic. And hopefully it will prepare you pretty well for the AP test in May. I hope you have a great rest of your day and good luck with all of your math.